Okay, welcome back everybody. In this week's video, we're going to be building the Growlight, this array that is assembled behind me. We needed a light to add to the aeroponics system that we built in the last two videos. So I thought to myself, how hard could it be to assemble that? And that's what we're going to do today. Now, for this project, I figured LEDs are highly efficient and they produce a lot of light. So I sketched up a schematic where we could power several hundred LEDs with a power source and a control unit, and I went ahead and built it. Now, for this light array in particular, I used three colors of LEDs, blue, green, and white. Now, the spectrum that plants need to grow is pretty wide, and clear LEDs cover a very broad spectrum of light. And I probably could have gotten away with just doing these, but I thought it would be interesting to combine several colors, so this is the choice that I went with. I also used just the standard 3.2 volt LEDs that I use for most of my projects. These aren't specific to plant growth, and perhaps a future version I will use higher powered LEDs, but I wanted to do a prototype to see how this all worked. And I'm pretty happy with the results. Now, this video will be broken up into several sections. We will start off by talking about the schematic designs for the control unit and all of the nodes. We'll talk about the code that runs our control unit. I'll go through some of the building steps from the frame to each of the nodes and the wiring, and then a pretty significant amount of troubleshooting. So yeah, I hope you guys enjoy it, and I just want to say thanks to everybody for all the really nice feedback on the last couple of videos. So, all right, let's get into it.
So here's a diagram of what each node looks like. Each node accepts 12 volts at the screw terminal. There's a 2 amp fuse built into every node. If there's some kind of short anywhere and a node starts to draw too much current, the fuse pops and the power to the entire node is shut off. 12 volts in along this rail, and each of the chains of 3 LEDs has a resistor and then a blue, clear, and green LED. I swapped the place of the resistor on each chain, alternating all the way up. And I did this in an attempt to stagger the position of the LEDs so that I would get a better spread of the light. So we did this 8 times. Each of the nodes has 11 chains of 3 LEDs for 33 in total times 8 is 264 LEDs in total. So now let's have a look at the more zoomed in diagram, a more detailed diagram of each of the chains I was talking about earlier. So each chain takes 12 volts. Each of the LEDs has a 3.2 volt forward voltage, 9.6 in total. So we use a 120 ohm resistor. Each of these is 3.2 volts at 20 milliamps or 0.02 amps, which makes 0.064 watts at each LED. We have 3 LEDs in each chain, which is about 0.192 watts per chain. There are 11 chains per node, which is about 2.112 watts every node, and we have 8 nodes in total. In total, about 16.896 watts for the whole system. And then now let's have a look at just a rough schematic of what everything looks like. So what we have is our 120 watt power supply, 12 volts, 10 amps, and our control circuit, and it provides 12 volts to each of our nodes. Now let's talk about the control unit. Here is a diagram of the control unit, peripherals that are attached to it. Outlined in green here is the perf board. Here we have our rotary encoder and our 4-segment 8x8 LED display. Up top here is our DC power source, the on-off switch, and then the push button, the shortcut button to flip the relay, independent of any of the programming, and it just allows us to make sure everything else is working in the circuit. Our circuit accepts a 12 volt DC source. These are screw terminals, as well as these two down here. So our circuit accepts a 12 volt DC source, which is fed into this screw terminal. That 12 volt source
is converted into 5 volts here in this voltage converter. I have two 220 microfarad capacitors attached to it to smooth out that signal so that we get a nice stable current for our processor. Okay, so 12 volts, 12 volt voltage in, the ground for the voltage regulator, and then 5 volts out, which is fed to this screw terminal, which we use to attach to our on-off switch. So when this switch is in the on position, feeds power into this screw terminal, and this screw terminal powers this 5 volt bus. And along this bus, we power the Arduino, the Pro Mini, through the raw pin on the Pro Mini. We feed it 5 volts. We also run that bus down to these 2 screw terminals, in addition to the ground, which power our rotary encoder and the 4-segment LED display. Now, as far as the light array goes, these 12 volts are fed into a mechanical relay here, which is typically in the off position. When the relay is activated and this arm flips over, this becomes a 12 volt bus, which powers these 8 screw terminals, each of which is connected to one of the lighting nodes. So the 8 lighting nodes we have in our rack are each powered here along the same bus. The same with the common ground here. They all connect back to the ground for our power source. Now, we control the power through this mechanical relay from 2 sources. I have the push button source, which is connected to the 5 volt bus. So when you push this down, it sends a 5 volt signal to the relay, which opens it. So we can just on off, make sure everything's working. That looks great. It's independent of any code. As far as the processor is concerned, we have connected the digital out pin number 4 to an NPN transistor. This pin will send a 40 milliamp signal at 5 volts, which is not strong enough to flip the relay over. So we send it to a transistor, which has 5 volts in the collector, and combined with the digital out signal, it emits a 5 volt signal strong enough to flip the relay over and turn on our light array. I've also added a snubber diode to the mechanical relay because when these coils are powered on, the moment that they shut off, the coil attempts to maintain a voltage. And this can cause strong negative voltage spikes in your circuit. And those spikes can damage sensitive components, i.e., microprocessors. So what you do is you add a snubber diode, is oriented in the opposite direction of the normal current flow, and it absorbs that power spike, hopefully protecting sensitive components like our microprocessor. As far as the peripherals go, they are powered from this 5 volt bus to these 2 screw terminals. The first of which is our rotary encoder. So we have the VCC and ground connected to this screw terminal. The SW, which is the up-down button on the rotary encoder. And then the digital pin and the clock. Those 3 pins are respectively connected to the 5, 3, and 2 pins, the digital in pins on the Arduino. Similar setup with our 4-segment display. There's a VCC and a ground connected to our 5 volt screw terminals here. And then the digital in, chip select, and clock pins, which are respectively connected to the 10, 11, and 13 pins, these digital inputs on the Arduino. That's the control unit and probably the most complex part of this whole assembly.
We wrote a short Arduino script, which is just C++, to manage the control unit. And I'm not going to go through the whole script because it's a couple hundred lines and I don't know if that's very useful. I will be posting a link to the code. I've published it on GitHub so anybody can download it and have a look at it if they'd like. More or less, we define all of the in-out pins. We set up the display. we set up some variables to manage setting the clock, the alarm on and alarm off. Then we handle the user input, the button input, and the rotary encoder. And then we have a couple of methods that turn the lights on, turn the lights off. And then we have some code that formats the time nicely for our display. And then these methods handle setting the hour and the minute for each one. This is the main method that handles the encoder input. And this, like all Arduino scripts, is a loop. So what happens is when the Arduino turns on, there's a short startup sequence here in our setup method. The interrupts are attached, the peripherals are attached, the lights turn on and off, the display turns on. The user first sets the time of day, then they set the time the lights come on, and then they set the time the lights come off, and they have to confirm at each step that has happened. And once that's done, then the control unit is running. So like I said, I'm not going to go through all this code. There will be a link to the GitHub page for anybody who wants to look at it. And if you're interested in contributing, it's open source. So yeah.
So we have all the parts laid out for the next step of our project, which is the lighting system. In front of me, I have each of the perf boards that we're going to use as nodes. We have the microcontroller, which is an ATmega 328, which we'll be able to program a voltage regulator, some transistors, and a relay. And the first thing I'm going to do now is assemble the first node and test it and see how it looks. We're going to be using white, blue, and green for the grow lamp, which are the wavelengths that I think will give us the most on the node. So what we have here is a rough mock-up of how each of the nodes is going to function for our light system. And what this is 7 chains of LEDs that are in series, and each series sit in parallel. So what I'm going to start doing is soldering together a node so that it functions in the same manner, and we're going to plug it in and see how it works. Okay, that's the first node. All of the LEDs assembled. I'm going to add the 2 amp fuse to this perf board, and then I think it started on soldering. Got everything soldered together. It was really tedious, and it looks okay. I'm not thrilled with how it came out, and boy, was it a lot of work. Okay, most of them work. It looks like some of those green ones, they don't look great. Looks like everything else works. I'm starting to second guess this approach. I'm going to move on and work on the next node. This workspace is getting messy, and the fan's not on. Okay. Put that 2 amp fuse in there. I'm disappointed that those lights were dim. It's kind of a bummer. I wish I had noticed that before I soldered them in place. I have 3 of the 8 nodes soldered and connected to a power supply. Everything's working. This was considerably more tedious than I had planned, and I'm just going to keep on moving. Got the 4th node soldered. Took me almost an hour to do. 6 nodes soldered together. I'm getting to be much quicker. It's only taken about 20 or 30 minutes. All right, 7 of 8 nodes soldered. This is looking pretty good. I don't know how well it shows up on camera, but it's really bright. So now that all 8 of the nodes are soldered together and everything seems to be running, we're going to build the scaffolding for the lights. And here is a shot with the lights off. but it is surprisingly bright. I'm hopeful that this is going to be functional. Everything is very bright. I'm very happy with this.
Done. It looks square. Looks square enough.
That frame is complete. So now we have this section, which is where each of the nodes will sit, and then down here our main controller unit and the power supply. So we have now arrived at the soldering stage, and we're going to assemble the controller here. Drew out as close to scale as I could manage a circuit diagram because it's going to be pretty tight on this board, and I wasn't really sure how I was going to fit everything together. Give it a try to draw on paper and see how I'm going to fit all these components on here. We have the entire circuit assembled on a series of breadboards here. I've been using an Uno with the processor removed to flash the Pro Mini. What I've done is I've coupled the RX and TX pins to the RX and TX pins on the serial header. This is the reset pin, this green cable. So this just acts as a USB to serial for the Pro Mini. We've got 12 volts coming in here, a voltage regulator to step it down to 5 volts, which is then fed into the raw pin on the ATmega 328. You can feed, I think it's 5 volts to 12 volts. And then what we got over here is a relay that will control the light array. We actually have a transistor and a relay. So we send a digital signal to the transistor, which fires the relay. I've got a couple LEDs here. They're just placeholders for the relay. We added a power switch and then a shortcut button. So what I'm going to do is I'm going to turn on the power. There's our startup sequence, just a little startup sequence there. And we've got our rotary encoder, which allows us to set the time of day, hours first, then minutes. Confirm. Now we'll set when we turn the lights on, hours first, then minutes, confirm, and then when the lights go off, hours first, then minutes, confirm. And then this is displaying our time of day. So this is going to run until it runs into the alarm, which is when we turn the lights off. I don't remember what it was. And then, like I said, I have my physical shortcut button. It's always nice to know that the circuit works. So that's it. That's the circuit. And it's time to get soldering.
Got most of the circuit assembled here. It looks pretty good. It got a little crazy in here. So the next thing that's going to happen is we're going to plug this into the light array and see if the startup sequence works.
so now we've got the peripherals attached. I'm kind of I don't know why I'm so much more nervous on this stage. It just feels like, it's the real thing now. I don't know. Anyway, so we're gonna get all this assembled. Ooh, this is dicey. I'm nervous. All right, cross your fingers. Oh, yes! Yes! Very cool. Uh-oh, that's getting a lot of signal. Oh no, what the heck is going on? That wasn't good. Okay, something's wrong with the encoder, or across the wire, or something crazy is going on. I'm gonna turn it off because this is freaking me out. Does the click work? Oh, the click works. That's weird. Oh boy. Oh boy, that could have been bad. I think I just got really lucky with my rotary encoder. Plugged it in upside down, which means it was getting all sorts of erroneous signals. Funny that the button worked. Oh, I guess the button's the middle pin, so it would have worked anyway. That makes sense. Let's try for pass number 2. Yes! Oh, look at that. All right, hours, minutes. Oh, let's set it for 1 minute from now and confirm. The encode. Did I plug it in backwards? I think I must have done something backwards because it's clockwise counting down, counterclockwise counting up. Anyway, let's see. 5. I think I must have crossed a wire. Let's turn that off. Good night. Should I turn it off? Okay, so a couple things. I did miss the wires up. The clock should be in pin 3. So we're just gonna pull this guy out. Okay, let's see, rotating clockwise. Great, and counterclockwise. All right, let's test the alarm now. Confirm, 1, 2, 3, 301, confirm. Assuming this works, I will now wire everything up and we'll see if the alarm circuit turns the lights on and off. If it does, good news. Then we'll put the control unit into its new home and we're going to install the buttons here and we'll just attach that there. You heard the relay go. Good. Then we'll, I think, trim up some of the wires and do a little bit of cleanup. What the heck? 1, 2, 3, 4, 5, 6, 7. Oh no! God! I'm 1 screw terminal short. Darn it. Man, I really thought I was done with soldering. That is a bummer. Oh man. I should just do that now. Okay, here I hope I have made the last, knock on wood, adjustments, or major adjustments at least. This is what the underside of the prototype board looks like. I just added this white connection. This allows, I don't know if you noticed a moment ago when we shut the power switch off, the screen remained on, is because the screen was directly connected to this, the 5-volt line. Instead now, both the microprocessor and the peripherals share a common 5-volt line together. So when we hit the power switch, it'll shut all of, like, essentially everything down here off. This is the light array. Let's see how this works. All right, it's all wired together. I'm a little nervous, but we're gonna turn this thing on. Plugged in. Okay, so far nothing terrifying. Oh, let's test that switch out, see if that, yeah. My hand was in the way, but this is good. Oh, this is all really good so far. Okay, but the big test is going to be, I'm going to set it to the time to 1, no minutes, confirm. The alarm will be at 1:01, confirm, and the alarm will shut off at 1:02. All right, now we're at 1. Okay, well, see if this thing works, baby.
Okay, there is obviously a major problem with my circuit. Shoot. Something is drawing too much current and everything is shutting down. You know, one more thing we can test is because we added this shortcut button into the circuit. If the power's on, when I hit this button, the entire light array should light up. Oh, yes! Oh, and it shut off. And it's on! And it shut off. What the heck is going on there? That makes me worried. I don't know how to explain that. All right, we gotta do some testing on the screw terminals and see if the current is dropping when I hold it open. Yeah, it does. What is that? Yeah, okay. There's like a huge current drop. This is a problem. Wonder if that snubber diode is backwards. Okay, so here's a little update on what's going on and what I think the problem was. I was using this power supply, which was 3 amps, 12 volts, so about 36 watts. And the light array should take around 20. But the thing is there's a fair amount of resistance in the system. I think I could have used better gauge wire for everything. I replaced the power cord that I had put together myself. I think that maybe there was some leakage there, some resistance. My point is this power supply was not sufficient enough. There wasn't anything wrong I could tell in the circuit other than the current draw was exceeding the capacity for this power supply. So what I've done is I have connected this power supply, which is 12 volts at 10 amps, so 120 watts, which is significantly more. It's overpowered for our project, but that's okay right now. So when I turn the relay on, no issues. I failed to consider how much resistance was in the system and how much power was being wasted. So that at least solves that problem. I'm gonna trim these wires, try to get everything situated. This power supply is too big for the frame that I created, so I'm gonna have to make some adjustments there, but at least we made a step forward. Okay, so most of the assembly is done. It's all kind of tied together. My desk is a mess. My office is a mess. It's a disaster in here, but this part's done. And I have just secured the screen to the front of the frame. And yep, it works. Everything's running. I was very nervous at the end. It was challenging to get everything to fit in, and I was worried it was gonna pop a solder off or something, but looks like everything's going together. I'm going to add a new piece of framing for this since it won't fit in this little trough over here. And then we're gonna hang this thing up. Okay, so apparently I can't get through a single video without blowing up one electrical component. And the component of the day was the voltage regulator. I made a little frame so this would be secured and in place, and when I plugged the VCC and the common back in, I switched them around, and this exploded in sort of spectacular fashion. It let off like a little puff of smoke. So now I need to take this all apart, desolder this voltage regulator, put a new voltage regulator in, put this all back together, and then I will hang this up. I don't have any video footage of that exploding. So going in, voltage, grounded, voltage, and then if I go ground, The output is nothing. So now I need to go in, get rid of this, and replace it. It's on there, but I'm not. It's not the prettiest thing I've ever assembled, but I really didn't want to take apart the underneath. If you recall from earlier parts of the video, the underside of this is quite complex in here, and taking that apart, and frankly taking all this apart, was more than I was willing to do. So, not very pretty, but capacitor's back, voltage regulator's back. We're gonna give this a shot and see what happens. All right, here we go. That was odd. So you saw the startup sequence go, but the display looked really bad. Oh, well, there's your problem. Okay, I'm gonna put those back together and then we're gonna start this over again. All right, cords put back together. Office, still a mess. Dead parts, plastic. This is bad. It's looked better in here before, but did we fix it? Look at that. Huh? Clock on, 3 hours, minutes, confirm, 2, 3, 4, clock off, or no, what is it first? Time of day. All right, this is clock on, and then this, minutes, confirm. So it's 3:03 in the morning. It's not really 3:03 in the morning. Okay, so we blew out some parts, check. We replaced the parts, check. It runs again. Feels like a win to me. I am done, I think, messing with this because every time I touch it, I blow something new up. So what we're gonna do is we're gonna get this thing strung up and I'm gonna call it good for this version of the project. Okay, that's a wrap on this build. I'm glad this is done. This was harder than I thought, and the result I'm satisfied with, but there were some things that I would like to improve on for the next build, and I'd definitely like to design a better frame, specifically something that has all the cords in mind. I didn't really think about that when I was designing it, which seems silly in retrospect, but you just think like, oh yeah, I'll just run the wires around the thing. But you know, when you get to the end, there's a lot going on back here, and I think there's a nicer way to kind of hide these or lay them in. So I'd like to design a better frame. I'd like to design a better way that the power supply maybe sits on the end like I'd initially designed. Maybe kind of have some of these inlaid better, but you know what? It works. It works. I'm happy this is done. I'd like to do another version and maybe a higher powered version. This might end up just being a light panel that I use for seeding, where I grow stuff that's very small and maybe doesn't require as much power, and then possibly use the next version, maybe the adult plants. I think it's showing up on the video. I got 1 or 2 of the nodes that are flickering, which is interesting. Not really sure what that's about. But there it is. What an adventure.